Hello, Honors Chemistry students. This is Mr. Spurk, and these are your Chapter 5, Section 1 notes, revisiting the atomic model. So the last we left off was with Rutherfords Model. However, there are some limitations to Rutherfords Model, and they're that it only explained a few properties of the atom, so sort of where things are located, but it does not explain chemical properties. For example, one of the big things that it couldn't explain was that it can't explain why objects glow dull red, then yellow, and then white when they are heated to higher temperatures. So because of this, they knew there were problems with Rutherford's model, so they began to investigate even further. So Niels Bohr was another chemist, and he changed Rutherford's model to include discoveries about how the energy of atoms change when the atom absorbs or emits light. He proposed that electrons are found only in specific circular paths or orbits around the nucleus. So similar to the Rutherford model where there's the nucleus with the proton and the neutron. However, the difference here is that these electrons, he's saying there are energy levels or orbits. So this we want to kind of think about our solar system as a good example. So Niels Bohr said that the electrons move around the nucleus in certain allowed circular orbits so that they have paths. And orbits are fixed, definite circular paths where electrons can be pinpointed. Each orbit has a fixed energy, and these are called energy levels. And a quantum of energy is the amount of energy required to move an electron from one energy level to another. So electrons exist in these orbits, and they can travel to other orbitals, but to do so, they need to receive a piece of energy, which we will call a quantum. So an electron receives a quantum of energy, it can move from one energy level to another. So then we have the Bohr model, and it's sort of like the rungs on the ladder here, and they represent those energy levels. And think about a ladder. A person cannot stand between the rungs. You can only stand on the rungs. And with the Bohr model, he said that electrons cannot exist between the energy levels. They can only exist within the energy level or on the rungs. And the energy levels are unequally spaced. As you see in the ladder, the higher energy levels are closer together. So again, you can see here that they are pretty spaced out, and as you go towards the top, they are much, much closer together. The quantum mechanical model. So this guy's name is Erwin Schrödinger. He used new theoretical calculations and experimental results to produce a mathematical equation that describes the behavior of electrons. And the equation describes the quantum mechanical model. And as you see here, we probably have lots of symbols, maybe some things that you haven't seen before. We have what we call Hamiltonian operators, wave functions. This is a bunch of crazy upper level calculus that we will not get into, but I just want you to see what this equation can look like. So like the Bohr model, the Schrödinger's model restricts the energy of electrons to certain values. However, it does not specify an exact path that the electron takes. So remember, in the Bohr model, there was that orbit, and that's the only path that the electron is on, where the quantum mechanical model says, yes, electrons have energy, but they do not have an exact path. The quantum mechanical model determines the allowed energies and the likely location of an electron. So we don't know exactly where it is, but we have a pretty good idea. And that's what we would talk about with probability. So probability describes the likely location of the electron. It's represented by what you see here on the right, an electron cloud. So we have our nucleus here in the center and an electron cloud around. This is the space where our electron most likely exists. The cloud is more dense where the probability of finding the electron is high. Schrödinger's equation also leads to a mathematical expression called an atomic orbital. An atomic orbital These are represented pictorially as a region of space in which there is a high probability of finding an electron. So like the electron cloud we just looked at, that showed us a map of where these electrons most probably are. An atomic orbital is basically the same thing, but because they are based on a mathematical expression, they are much more accurate than just a big overall electron cloud. So we have these things called principal quantum numbers, and they're represented by the lowercase n. And these are the energy levels of electrons in the quantum mechanical model. And they are related to the periods on the periodic table. And remember that periods are the horizontal rows on the periodic table. So for each principal energy level greater than 1, there are several orbitals with different shapes, so different maps of where the electrons may be. These energy levels within a principal energy level constitute energy sublevels. So we have levels within principal energy levels, which then have sublevels. And each sublevel corresponds to orbitals of different shapes. And again, these shapes map the probability of where electrons are. So we're going to see these shapes on the next few slides, and just keep in mind that these aren't telling us exactly where the electrons are, because we can't know that, but we do have a mathematical expression that tells us where they probably are, or most likely are. So orbital shapes are denoted by letters. So for example, here we have an s orbital, and you see you have your x, y, and your z axis. So most often most likely you've probably only seen x and y axes. Now we have z. This gives us three-dimensional space. So an s orbital is just a sphere. And a p orbital, or more specifically a px orbital, because it's along the x-axis, is shaped like a dumbbell. So again, these are maps of where the electrons probably exist. So for given principal energy levels greater than 1, or anything below row 1 on the periodic table, there can be 1 s and up to 3 p orbitals. So for example, that would look something like this. Here we have our s orbital, here's px, here's py, and pz. And again, these second little letters here with the subscripts, those are denoted as what axis the dumbbell lies on. Then we have d orbitals. 4 of the 5 d orbitals have the same shape, but different orientations in space. So you see here, the first 4, 1, 2, 3, 4, these look like flowers. And then this last d orbital has quite a pretty wonky shape. They look quite crazy. But again, these are maps of where these electrons probably exist. So for a given principal energy level greater than 3, or row 3 and below on the periodic table, there is 1 s orbital, 3 p, and up to 5 d orbitals. So all of these shapes, all of this map can exist, and when you superimpose them on top of each other, that's what creates our electron cloud. So here's a summary of the principal energy levels and sublevels. This is going to come in quite handy on your homework and as we continue to go through the rest of the chapter and really the rest of the year. So again, you have your principal energy levels, and these refer mostly to the rows on the periodic table. So n equals 1 is row 1, n equals 2 is row 2, n equals 3, row 3, n equals 4 is for rows 4 through 7. Within those, they have this number of sublevels. Then within the sublevels, here are the types of sublevels. And within those sublevels, it tells you how many electrons can occupy that space. And we will dive into this a little bit deeper. The principal quantum number n, so again, remember that means the energy level, always equals the number of sublevels within that principal energy level. So if it's n equals 1, then there is 1 sublevel within that principal energy level. The number of orbitals in the principal energy level is equal to n squared. And if you look back at this chart and play around with the n and the n equals 2, you'll see that that holds true. So the last bullet here says that a maximum of 2 electrons can occupy an orbital, and the max number of electrons in a principal energy level equals 2n squared. So again, we will dive a little bit deeper into this over the coming days. I know that this is brand new, can seem a little confusing. Let's just keep on working through. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great day.